So in this video, I'll go over the 5R covering lemma, which you may have seen a version of in your measure theory class, although here I'm going to discuss it for a general metric space. It's not just Euclidean space. So suppose we have a metric space X and we're given a collection of balls. So I've illustrated an example here in blue of a random collection of balls. The 5R, and suppose that this collection, the supremum over all radii of the balls in this collection is finite. And the 5R covering lemma says we can pick a subcollection of these so that first of all they are disjoint. So for example in this figure, from the original collection of blue balls, I've highlighted a subcollection of disjoint balls. And not only are disjoint, they have the property that if I look at the balls with the same centers but 5 times the radius for the balls in this new collection, the union of these inflated balls cover the balls in the original collection. So you'll see here these shaded red balls are these red balls with the same centers but 5 times the radius, and you'll see that every ball, whether it's red or blue, is contained in this shaded region. So let's see an example of how the 5R covering lemma is used in practice. So you may have seen it used to prove the Hardy-Lewis maximal inequality for Lebesgue measure. However, because the 5R covering lemma works in metric spaces, we can actually generalize it to a wider class of measures. So in fact, a Hardy-Lewis inequality holds for doubling measures in arbitrary metric spaces. So we recall that a measure is said to be a C doubling measure for some constant C on the metric space X if whenever I have a ball B in my metric space, if I look at the double of the ball, 2B, so that's the ball with same center but twice the radius, then the measure of this double is no more than some constant times the measure of the original ball. And this holds for all balls with the same constant C. So then, if I define a maximal function like I did before with Lebesgue measure, although instead now I take averages with respect to my doubling measure, then I get a Hardy-Lewis weak type inequality just as before. So let's go over the proof of this, which is very similar to the proof for Lebesgue measure. So again, I'm going to call this set E lambda, and so my goal is to estimate the measure of this set. I'm going to assume again without loss of generality that f is non-negative. And now notice that for all x in E lambda, okay, so if x is in E lambda, that means that the maximal function is bigger than lambda. So the supremum of these averages over balls centered at x is bigger than lambda. So that implies there exists a ball, bx, centered at x, such that the average over bx of f d mu is bigger than lambda. All right, so I'm going to let curly b denote the collection of these balls. Okay, so notice automatically that E lambda is covered in the union of these balls, since every point in E lambda is a center of a ball from this collection. So the 5R covering lemma implies that there exists a smaller subcollection of disjoint balls such that, what do we have? We have that, so recall that E lambda is contained in the union over balls in this collection. And by the 5R covering lemma, this union is contained in the union over 5 times the balls in B prime. So thus, now we can estimate the measure of E lambda. So E lambda in measure by subadditivity of, so also I should use the mu measure. So the mu measure of E lambda by subadditivity, this is at most the sum over balls in curly B prime of the measure of 5b. And now by the doubling property, okay, so notice that the doubling property is for double balls. However, you can show that it implies a similar inequality if I look at 5b instead of 2b. So it implies that there's some constant depending on this doubling constant c, so that the measure of each of these balls is at most constant times the measure of B. Now, recall from up here, each ball in the collection B, and hence every ball in the collection B prime, satisfies this inequality. So thus, if I multiply both sides of this inequality by the measure of B and divide both sides by lambda, I get that the measure of B is at most lambda to the minus 1, the integral over B of f. Okay, and now because the balls in this collection are disjoint, this is at most the integral over the union of all the balls. However, the union is just at most the whole metric space. And now I have the Hardy-Lilliard maximum inequality, that the measure of this set is at most lambda to the minus 1 times the L1 norm of f.